A together just to make sure everybody is getting the ideas behind this because it's important. So for part A, first thing we're supposed to do is sketch the derivative function. Just by looking at the picture of f, try to sketch its derivative. So the trick here is to think about when is the derivative 0, when is it positive, when is it negative, okay? And think about big and small as opposed to specific values, right? The only specific value that we're really interested is 0, slope of 0. So where in this picture does the function f have a tangent line with slope 0? At the vertex, yep. And what is the x coordinate at the vertex? 0, right? Okay, so when x is 0, so I'm plotting x and slope of the tangent line. So I'm going to label that m just to remind myself. So when x is 0, slope is 0, so I have the point 0, 0. All right, now I'm going to look to the left of that horizontal tangent line for negative x values. And what do my tangent lines look like here? Positive or negative? They're negative, and they start out very negative, and they're getting less and less steep, right? So that means they start out very big, negatively, and they're approaching 0. Okay, so they start out very negative and approach 0. And then after 0, they get more and more positive. First, they're just small, and then they get steeper and steeper and steeper. Okay, so there's a picture. And I heard a lot of debate about whether or not that derivative function should have some kind of curve to it. It's very hard to tell when you're drawing a qualitative picture if there should be any kind of curvature to that derivative function. So if you had drawn that with a little bit of a curve, that would be a reasonable thing to draw. Okay. And the more you do this, the more you're going to get used to sort of knowing when there's a curve and when there's not. But that's why we have the calculator to help us, and the algebraic formula, the limit formula, to help us come up with a real formula for the derivative function. So first we go to y equals, and I'm going to put the original function in there, which is 0.5 x squared minus 4. And then in y2, I want it to graph the derivative for me. So I'm going to do math 8, which is n deriv, bars, y bars, function y1, comma, x. And some people with a little bit of a newer version of this calculator have to put in the notation a little bit differently. You're still putting in 2 x's and a y1. You just have to figure out where to put them. Okay, and I'm going to have this derivative graph a bold line so I can tell the difference. Zoom 6. Okay, so there's my function f, and here is its derivative f prime of x. And it does, in fact, look like a straight line. Okay, so then the last piece of this question is to use algebra and the definition of the derivative, which is this, the limit of the difference quotient, to find a formula for the derivative function. So we have the limit as h approaches 0 of f of x plus h minus f of x all over h. And remember, f of x is 1/2 x squared minus 4. So what the limit definition says is I have to plug in an x plus h. It's the first thing. So I have the limit as h approaches 0. F of x plus h would be 1/2 times x plus h squared minus 4 minus f of x, which is 1/2 x squared minus 4. And all over h. I put parentheses around the formula for f of x because I'm subtracting the whole thing. You could also put parentheses around the f of x plus h. Just doesn't make any difference calculation-wise. Okay, so this is the limit as h approaches 0 of, now I'm going to simplify the stuff in the difference quotient. X plus h squared, that's x squared plus 2xh plus h squared. So I have 1/2 x squared. You know what, I'm just going to do each step one at a time because that's sort of your best bet to avoid making mistakes. So first thing, I'm just going to square the x plus h. I have 1/2 times x squared plus 2xh plus h squared. Then minus 4 minus 1/2 x squared minus 4 all over h. Then I'm going to distribute my 1/2. And maybe in the same step, I'll distribute my negative sign. Limit as h approaches 0 of 1/2 x squared plus xh plus h squared minus 4. Yes, thank you. 1/2 h squared minus 4 minus 1/2 x squared plus 4 all over h. So now I'm going to combine like terms, and I have a couple of nice things happening where anything that has just a plain x or is just a plain constant is canceling out. My 1/2 x squared and my negative 1/2 x squared cancel. I have a minus 4 and a plus 4. So that leaves me with the limit as h approaches 0 of xh plus 1/2 h squared all over h. I still can't plug in my h equals 0 because I still get 0 over 0, but I can factor out an h from the numerator and then cancel with the denominator. So this is the limit as h approaches 0. Factor an h from the numerator, and I have x plus 1/2 h all over h. The h's cancel. Limit as h approaches 0 of x plus 1/2 h. Now I can take the limit. Now I can plug in h equals 0, and what do I get? X. When h equals 0, that whole term just disappears, and you get x. That is my derivative f prime of x. It's my derivative function, which looks very much like the graph that we sketched by hand and the graph that the calculator produced. Y equals x. The next one, the algebra involved in that limit definition, is a little bit more gymnastic, right? You have to do a little bit more. It involves some cubing and some factoring with cubes, but same general idea. Just keep chipping away at the difference quotient until you get the h's to cancel. All right, we ready to move on? Okay. So today we're going to briefly review 3 kinds of functions, and we're going to discuss the concept of continuity. Okay. So our 3 functions are going to be power functions, polynomial functions, and rational functions. You should be familiar with these from previous classes. A power function has the form f of x equals k times x to the p, where k and p are constants. They're just numbers. And they can be any numbers: fractions, decimals, whole numbers, integers. So for example, 3x to the fifth is a power function. Negative 2 square root x is a power function. How can I call square root x a power function? Because it's x to the 1/2. So this would be negative 2 x to the 1/2. And now it looks like k times x to the p. Right. But x squared plus 7 and 2 to the x are not power functions. X squared plus 7 because it's got this plus 7 term. And 2 to the x because the x is in the exponent, not the base. Right? For a power function, x is the base and the exponent is a number. What kind of function is this called? Anybody remember? Exponential, yeah. We'll review those on another day. Polynomial functions have this general form. So it's coefficients and integer powers of x. It's a sum of coefficients multiplied by integer powers of x. So for example, this is a polynomial. Negative 7x to the fifth plus 2x to the fourth minus 3x squared plus 4x plus 18. It looks like a sum of power functions, but the powers have to be positive integers. Right. A rational function is a ratio of two polynomials, one polynomial over another. Call that a rational function. All right, so below are the graphs of different power functions. Let's see if we can come up with a possible formula for each of these. So what does this one look like? X squared. How about this next one? Negative x squared, yeah. If you just throw a negative in front of any function, it causes a reflection over the x-axis. How about the third one? Y equals x cubed. Just one of the standard parent functions whose graph you should be familiar with. How about the next one? Negative x cubed. This looks like it was just another reflection over the x-axis. How about the next row, this first one? Square root x. How about the other one? The negative square root of x would be a reflection over the x-axis, so it would be like down here. It looks a lot like square root x, right? If I hadn't drawn this part over here, you might be tempted to call it square root x, right? Just by its qualitative picture. But why is it that the square root x has a domain of only x's 0 to infinity? Because you can't have a negative root, right? If you're taking an even root, right? If you're taking an odd root, you can have negative infinity to infinity as your domain. So you said earlier, cube root of x? Could be. Yep. It looks an awful lot like the root function, like if you ignore the left side, looks like it's a root. And it has to be odd because it has a negative infinity to infinity domain. All right, how about the second to last one? Close. What's 1 over x? Yeah, this is 1 over x. Yep. So when x gets really big, when the x's are getting really big, the y values are getting really small because the denominator is growing, which makes the value of the fraction smaller. So that's why we're coming down towards 0 here. And when x is really small, when x is approaching 0, when the denominator gets really small, the value of the fraction gets really big. Because like 0.1 goes into 1 10 times, and 0.1 goes into 1 100 times. So those values are getting really big, so it's blowing up to infinity. What do you think about the next one? 1 over x squared. It looks a lot like the one before it, at least the right-hand side does. And the x squared means that everything will always be positive. No matter what x value you plug in, we're going to square it, which means that the resulting fraction will always be positive. So everything's above the x-axis. Good. So we can look at the end behavior of polynomials. Let's use some good limit notation to describe the end behavior of negative 7x to the fifth plus 2x to the fourth minus 3x squared plus 4x plus 18. All right, before we do it with limit notation, let's do it with our arms. Here, 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 or here. Put your arms in the right end behavior. Right. So which arm's up? Well, I'm looking at you guys. You guys put your arms, not me. You can. Okay, like this. Yeah, yeah, good. So it's got to look like something like that. Left arm up, right arm down. Good. How did you know that? So you knew that it was going to have the same end behavior as negative x cubed. Good. Because the power is odd, the degree is odd, so all odd degree polynomials either have left arm up, right arm down, or right arm up, left arm down, and then the negative sign tells you which arm's up. Right? Okay, so if I'm going to do this with good limit notation, we would say the limit as x approaches infinity of the function f of x would be what? Negative infinity, because the right arm goes down, right? And we would say the limit as x approaches negative infinity to get the end behavior at the other end of f of x equals infinity. Good. Okay, so for a rational function, the end behavior is governed by the ratio of the leading terms on the top and the bottom. Okay, so there's three cases for the leading terms. If the degree of p is greater than the degree of q, there's no horizontal asymptote. If the degree of p is less than the degree of q, then y equals 0, which is the x-axis, is the horizontal asymptote. And if the degrees are equal, then the horizontal asymptote is the quotient of the leading coefficients. Does that sound familiar? Everybody's looked at some rational functions before? Okay, well, we're going to come back to them in a few minutes. Also, rational functions have vertical asymptotes whenever the bottom is equal to 0. You have a vertical asymptote. Unless the top is also equal to 0 at that number, and then you just have, what? A hole. Yeah, good. All right, so here's an example. We have a function, a rational function. We want to find all its asymptotes and its zeros, and we're going to make a sign chart of when it's positive and when it's negative, and try to sketch the graph. So first thing I'm going to do is just factor everything. X cubed plus x squared minus 12x. Well, I can factor out an x, and I get x squared plus x minus 12. And I can factor out an x from the bottom also. And I have 2x squared plus 13x plus 6. So I can cancel the x's. Can I factor any further? I think this would factor, right? Plus 4 minus 3. How about my denominator? Can that factor? It would have to be a 2x and an x. And my last entries would have to multiply to 6. Oh, I think 6 and 1 would work. Because then I have 12x plus 1x gets me the 13x. So that's it. Nothing else cancels, right? All right, so asymptotes, right? Asymptotes, we have vertical asymptotes when the denominator is 0, right? So vertical asymptotes, set the denominator equal to 0 and solve. So we would have x equals -1/2 and x equals -6. So I'll draw those in. Draw them as dashed lines because they're not actually part of the graph. They're just guidelines. Okay. And zeros are places where the function equals 0. So I would want to solve r of x equals 0. And r is a fraction, and when are fractions equal to 0? When the numerator is 0. So all I have to do is set the numerator equal to 0. And we get x equals -4 and 3. So I'll put those in as my zeros, -4 and 3. All right, and then the last thing I need before I start making my sign chart is asymptotes. So what can you say, I'm sorry, horizontal asymptotes. What can you say about the degree of the numerator and the denominator? They're the same. So the rule, right, was when they have the same degree, you have a horizontal asymptote that is the quotient of the leading coefficients. So my leading coefficient on the top is a 1, on the bottom is a 2. So my horizontal asymptote would be at 1/2. So I put in my horizontal asymptote at 1/2. All right, so next thing I have to do is make a sign chart. And I need another blank page here. So my sign chart is going to help me determine when this function is positive and when it's negative, because we can tell by looking at the factors. We have 4 factors here, 2 on the top, 2 on the bottom. When you multiply and divide stuff, you have rules for dealing with negatives, right? Negative times negative is positive. So we're going to look at when each of the factors is positive and negative, and then when we combine them all, we'll just use the rules of multiplying positives and negatives to see what the final thing is. So I'm going to draw on a big number line. And I'm going to analyze each of my 4 factors. So I'll start with x plus 4. I'll do them each in a different color. When does x plus 4 equal 0? At -4. So I'm going to put in a fence at -4. And to the left of -4, what is the sign of the factor x plus 4? Negative. Anything I plug into x plus 4 that's less than -4 will always give me a negative. So I'm going to put negative signs over here. And when I plug in something bigger than -4 into that factor, I get positives. All right, next factor, x minus 3. Where does x minus 3 equal 0? At 3. So I'm going to put in a fence at 3. Okay, when I plug in to x minus 3, something to the left of 3, what's the sign of that factor? Negative. So I put in all negative signs over here. And when I plug in something to the right of 3, x minus 3 will be positive. Positive signs over here. Next factor, 2x plus 1. Where does 2x plus 1 equal 0? Negative 1/2. So that's right here. I'm going to put in a fence there. To the left of negative 1/2, when I plug into 2x plus 1, what do I get? Positive or negative? Negative. You can pick any test point like negative 10, right? Plug a negative 10 in there, you get negative 20 plus 1 is negative 19, negative. So anywhere to the left of negative 1/2, we get negatives. And to the right of negative 1/2, I'm going to get positives. You pick any test number just to check. 2 times 0 plus 1 is positive, right? Okay, and then my last factor, x plus 6. Where does x plus 6 equal 0? Negative 6. So I'm going to put in a fence there. And to the left of negative 6, x plus 6 is negative. And to the right, it's positive. Okay, now I'm going to analyze my r of x function as a product quotient of those 4 factors. Product and quotient of those 4 factors. And the rules for multiplication and division dealing with positive and negative signs are all the same, so we can do it all together. So it looks like when we're to the left of negative 6, every one of my 4 factors is negative, which means when I multiply these two and divide by the product of these two, what will my quotient be? Positive. Negative times negative divided by another negative times a negative, we get a positive. Between negative 6 and negative 4, I have negative, 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 positive. What's my quotient going to be? Negative. 3 negatives and a positive will make a negative. Between negative 4 and negative 1/2, I have positive, negative, negative, positive. R of x will come out positive. Between negative 1/2 and 3, positive, negative, positive, positive, negative. And then from 3 on, all my factors are positive, so R of x will be positive. Just extend my fences here. Okay, so now I know when the function will be positive and when it will be negative. This will help me graph the function. Okay, so to the left of negative 6, I know that my function is always positive. So that means I'm going to use the guidelines I've already drawn. These are asymptotes that I'm going to approach but not cross. And I have to always be positive, so I can't draw anything down here. So it's probably going to look something like this, because it has to approach both of those asymptotes and always be positive. All right, let's see. My next interval of interest looks like it's between negative 6 and negative 4. Oops. Negative 6 to negative 4 is always negative. So it's probably like that. It's because I have to be below the x-axis and I have to approach that asymptote. And then from negative 4 to negative 1/2, it's positive. Oops. Negative 4 to negative 1/2, positive. Is that right? Oh, yeah, okay. Yeah, so it's going to go up, but is it going to cross that asymptote? Well, maybe we should plot a point to find out. Like maybe the y-intercept would be interesting. What do I get here when I plug 0 into the top and the bottom? 0. Okay, so I have a hole at 0. Pick another value. What do you get if you plug in like negative 2? Let's see. Okay, x cubed plus x squared minus 12x plug in -2, I get 0.833. So it looks like I crossed the -1/2 value here. Up there. And if I plug in 0 after I factor and cancel the x's, I would get a -2, right? -12/6 would be -2. So I would have I have a hole here at -2. 0, -2. So that goes like that. And then -1/2 to 3 is always negative. -1/2 to 3 is always negative. So this looks like maybe it goes like this. Oh no, it can't. Oh, at 3 it's 0, and then after 3 it's always positive. Yeah. So that goes like that. And then the question is, what happens between -2 and -1/2 here? It has to be positive, right? From up to -1/2 has to be positive. And we have a vertical asymptote, so it must approach that asymptote at some point like that. And then this must go down towards the asymptote on the other side.
It can at that point.
That's a great question. Why did we cross the horizontal asymptote? So the idea behind a horizontal asymptote is that the horizontal asymptote tells you end behavior. So it's an asymptote that the graph approaches at its ends. So you can cross it locally. That just governs end behavior. So there's actually quite a lot of calculus in this, in determining when the function blows up and when it goes down to infinity. So when I think about why is the behavior look like this as I approach -6, well, what happens as x gets close to -6 is that this factor of my function gets close to 0, which is forcing my whole denominator to get close to 0, which is making the value of the whole function get really big, right? Because when your denominator gets small, the function gets big. So we've got behavior of the function going to infinity at -6. Okay. So there's a reference sheet just before the learning objectives at the end of this class on graphing rational functions, created by another GCC math teacher, Lee McGee. All right, so we're going to change gears a little bit now, talk about a property of some functions called continuity. So roughly speaking, a function is continuous on an interval if you can draw it without picking up your pencil. That's sort of a colloquial, everyday English definition. In a more rigorous mathematical sense, a function is said to be continuous at x equals c if it meets these 3 criteria. F has to be defined at c, has to have a value. The limit as x approaches c of f of x has to exist. And the limit as x approaches c of the function has to equal the function value. Okay, so there are 4 basic ways for a function to be discontinuous at a point. So we want to identify why the function is discontinuous at C using the rigorous definition. Like what part of the definition has failed in part A? F isn't defined at C, right? Part 1 of the definition failed. F of C does not exist. How about part B? What part of the definition has failed here? The limit doesn't exist, right? Because as we approach C from the left and as you approach C from the right, they're approaching two different values. So the limit doesn't exist. For part C, does the function value, is the function defined at x equals C? Yeah. Does the limit exist? Depends on the textbook you're looking at. Some textbooks would say that the limit is infinity. Some textbooks say that infinite limits are in the does not exist category. Okay. But either way, does the limit equal the function value? No. So we could say 2 or 3 here are the reason for failure. Depends if you call infinite limits existing or not. Okay, how about part D? Reason number 2, the limit doesn't exist? The limit as x approaches C, the limit from the left and the limit from the right, are they approaching the same y value? Yeah. It's 3. Number 1, the function is defined. There is a value of the function at C. So at C, there is a y value. The limit from the left equals the limit from the right, but they're not the same, right? The two values that the function is approaching as x gets close to C and the value of the function at C are two different values. They're not equal, so 3 is the reason it fails. Mm-hmm. Oh, okay, yeah, so sure. If we said the limit as x approaches C of f of x, we could say it's infinity, right? And then we would say, but f of C is some y value. We'll call it, I don't know, capital F for function value. So f does not equal infinity, right? The function value does not equal infinity, so that's part 3 is failing. Okay. So you can have a hole, you can have a jump, you can have a vertical asymptote, or you can have a hole, but even though the function is defined, it's not defined at the same place the function is going. Okay, so here's a nice piecewise function, and we want to make sure that it's continuous on all real numbers. We want to find the value of k that will make it continuous. So no matter what I make k, the first piece there is going to be k squared minus 3x. It's just some number minus 3x, which is going to look like what? What's its graph look like? K is just a number, like 25 minus 3x. It's going to be a line, right? It's going to be a line, right? Because k is just a number, a constant, yeah. And then look at this next part. For k, any number, some number like 5 times x minus 1 squared. What's that going to look like? That's a parabola, okay. So are lines in general continuous? Yeah, are parabolas in general continuous? Yeah. So both of those things, if they were by themselves, if they were independent, would be continuous. So what's the only x value I really need to concern myself with about it being continuous there? 2, the place where I switch from one formula to the other. I have to make sure that that spot is continuous, because everywhere else, to the right of 2, it's going to be continuous because it's a line. To the left of 2, it's going to be continuous because it's a parabola. I have to make sure that those two, the line and the parabola, meet up. All right, so I need the limit as x approaches 2 of f of x to equal f of 2. I need the limit to exist, and I need it to be the same as the value of the function. What is the value of the function at x equals 2? Yeah, can you explain how you got that? Yep, when x equals 2, that means we're going to use the bottom line because this is for x is less than or equal to 2. If you plug a 2 in there, 2 minus 1 is 1, squared is 1, k times 1 is k. All right, so f of 2 equals k. So I need the limit as x approaches 2 of f of x to be k. So when I approach from the left, I'm going to be approaching along this parabola. And that one's going to be fine because I know that at the value it's 2, and I know that parabolas are continuous, so that way is fine. I need that my line needs to, so when I approach from the right, I need my line to approach 2, to approach k as x approaches 2. So how can I make sure that that happens? Yeah. Okay, so if I go from, it needs to be from both sides, right? From the left, we know is fine. And I need to make sure that the limit as x approaches 2 from the right, which means using the formula k squared minus 3k, 3x, has to be k. So when you're taking limits, what's like the thing you do first? Substitute the value in. So if I substitute a 2 in here, I would get k squared minus 6. I have to make sure that equals k. Can I figure out a k that would make that true? 3? 3 squared is 9 minus 6 is 3. Sure. Any other k's that would work? No. Negative 2? Negative 2 squared is 4 minus 6 is negative 2. How could I, is there some way, some tool I have that I could have solved this equation without just thinking of the solutions? Factor, I could move the k over, factor, or use a quadratic formula. It's just a quadratic equation. We get 3 and negative 2. Either of those k values should make my function continuous. So let's take a little look at an animation of this problem. Okay, so blue is the parabola, k times 1 minus x squared, and red is the line, and the parabola is what I graph to the left of 2. The red line is what you graph to the right of 2. And here's my k value over here. Right now k is 2. So I'm just going to drag k till I get to 3. Close enough. And now you see they touch. So if we choose k equals 3, this function is now continuous. The limit from the left and the limit from the right both equal the value of the function. All right, so now let's see what happens when k is -2. Let's see if that works. Oops. Oh, look, that one works also. When k equals -2, the function is continuous again. That make sense? All right, last thing. The intermediate value theorem is continuous. The intermediate value theorem says that if f is continuous on a closed interval a to b, so that means on an interval from a to b, including the endpoints a and b, and k is any y value, right? K is any number between f of a and f of b, then there exists at least one c between a and b such that f of c equals k. So if I draw a picture, this theorem becomes like, well, duh, right? So when I draw a picture, I have a closed interval, a to b, right? An interval on the x-axis from a to b. And the function is continuous on that interval. I can draw the whole thing without picking up my pencil. It says that if you pick any number k between f of a and f of b, so pick any number, so say right here, pick k between f of a and f of b, the y values at a and at b, then there should be at least one c, maybe more c's between a and b, so that f of c equals k, right? And it turns out that in this case there are 3, right here. So if I draw this horizontal line, there's 1, 2, 3 values c between a and b, so that when I plug those x values into the function, I get k. Make sense? Now the continuity thing is really important, right, in order for this to be true, because I could draw a function a, b, that looks like this. Could be. So then if I choose some k between f of a and f of b, so go up to my graph, here's f of a, here's f of b. Now if I choose a k value in between, there's no c, right? There's no c in between a and b that will give me that k value. So the continuity thing is really important, but when you have it, just looking at this picture, it's like, obviously, there's going to be a c, right? So your calculator has a root finder in the calculate menu. We're going to find a root using the intermediate value theorem. To 2 decimal places of accuracy, I want to find a root of x cubed minus x minus 1 equals 0. That means a solution to this equation on the interval 0 to 2. But before we even start, I want to prove, using the intermediate value theorem, that there is one there. Before I even have my calculator look for it, I want to know that there is one to find. So I'm going to let f of x equal x cubed minus x minus 1. And if I take f of 0, what do I get? -1. And if I take f of 2, which is the other endpoint of my interval, 0 to 2, what do you get when you plug 2 in? 5. Okay, so f of 0 is -1. So if I wanted to, draw a little sketch here. I now have 2 points. F of 0 is -1. F of 2 is 5. And x cubed minus x minus 1, is that a continuous function? Yeah, so that means that it has to cross the x-axis somewhere. I have to be able to connect this point to this point without picking up my pencil. Then I have to go through the x-axis. So that's what the intermediate value theorem says. In this case, my k is 0. There has to be some point between 0 and 2 that when I plug it into the function, I get 0. So then I can have my calculator do it. Now that I know for sure it's there, because the intermediate value theorem guarantees it, we just type it into y1, x cubed minus x minus 1. It looks like it's somewhere between 1 and 2, so I do second calc, choose option 2, 0, left bound, right bound, and a guess. And it's about 1.32. So your calculator uses the intermediate value theorem when it's finding those roots, because it searches. You give it a left bound and a right bound and a guess. So if you give it this left bound and this right bound and this guess, say, it just goes left to right, making smaller and smaller intervals, and seeing that one, like negative, positive, negative, positive, negative, positive, and it zeroes in on the 0 by seeing that one side's negative, one side's positive. All right, any questions? Okay, and we are just about out of time. So I'm going to have you work on this activity on your own. Please work on it. Get these done over the next few days. They're a really important review, so spend a little bit of time on them. And let me know if you have any questions. We can go over a couple of them in the next class or two.